Alright guys, here we go. We are going to start up again with the second part of Chapter 7, and today is going to be all about solubility, what affects it, like what can we determine out that, like what does the nature of something have to do with solubility. Mostly we're going to be looking at the differences of solids and gases. That's one thing I really want you guys to clue in, and we're going to learn a little bit more of scientific literacy, learning how to read a graph, and get information out of that. So let's, without any further ado, let's just dig into solubility for today. You want to? Alright, so the first thing we're going to look at are the factors that affect solubility. Like things that make stuff more or less soluble. And the first thing that we're going to look at is the nature of the solute and the solvent. Now this is something you really can't tweak. Nothing you can do about this, right? So here's the deal. It's the intermolecular forces of attraction, they have to exist for there to be dissolving happening, right? Sort of. For the most part. So if you have something, for example, if you have something that's polar, right? Like a polar solvent, like, dare I say, H2O, right? If you remember, water looks like this, right? Very, very polar. There's one end that's slightly negative. There's one end that is slightly positive. You guys remember that? So water acts like a little magnet when you throw it in there. If you have a polar solvent, it's going to be really good at dissolving polar and ionic solutes, right? Because you have a little negative region and a little positive region. It acts like magnets, and they all kind of just stick together. It's quite literally like throwing a bunch of magnets into a box. They all just stick together. Does that make sense? And the way dissolving happens, like what happens when something dissolves, is that these intermolecular forces of attraction between the solvent and the solute, it totally overcomes those ionic bonds or whatever kind of intermolecular forces of attraction were holding the solute together, gets broken apart. It's just they get overwhelmed by the intermolecular force of attraction between the solvent and the solute. Which is why sometimes some things dissolve and some don't. It's all a matter of the relative strength of the intermolecular force of attraction, or those ionic bonds, as compared to the solvent-solute attraction. And if the solvent and solute force of attraction is greater than or can overwhelm those ionic bonds, off it goes and it totally dissolves. You understand what I'm saying? I think you do. So look, once again, let's go back to this thing where we look at how water arranges itself around ions. And there are two models, right? We've got the football model, where you just say positive end, negative end, super easy. And then there's what I call the Mickey Mouse model, where we have an oxygen, which is a circle, and hydrogen, two dots, right? And now this one, the Mickey Mouse, we have to keep in mind, this is something we have to use our noodle for, to know that this side is going to be the negative end and this side is going to be the positive end, right? Because there's one oxygen and two hydrogens. So if we were to draw them, let's do the football around the hydrogen. There's my football, and what end will be attracted to the positive ion? You guessed it, the negative end of the water. And remember, this is this happens in 3 dimensions, so it's not just a flat, daisy looking thing. It's the entire surface, all around, front, back, top, bottom, left, right. Oops, not thinking. Right, so the entire ion gets surrounded by water molecules, and that's kind of how it's able to overwhelm those ionic bonds, because it's not just one little teeny intermolecular force of attraction here. It's here and here and here and here and here and here, and all the ones in the front and all the ones on the back and left and right. It's just, they add up. You know what I mean? It's sort of like death by 1,000 paper cuts. Now, same thing, only completely different over here at the chlorine. Now, the chlorine is negative, so that tells me that probably the positive end of the water is going to stick to this guy, right? And the waters will arrange themselves this way around this negatively charged chlorine. There. Look familiar? It should, because we have done this before. But now we're looking at it from a solution perspective, right? Alright, so that's one way that polar and ionic things are able to dissolve with each other, is that like the polar and the ionic, they have charged parts. They act like little magnets, so they have really strong intermolecular forces of attraction, so they can stick to each other and kind of like make stuff happen. Now, the opposite situation we have is nonpolar substances. Now, if something is nonpolar, that means that there are no intermolecular forces of attraction. There's nothing kind of like holding them together, right? And so the way that this happens, so for like nonpolar things, that would be like oil and butter and things like that. The reason why they can dissolve together is because the intermolecular force of attraction are basically too weak to keep the particles from mixing together. There's no intermolecular force of attraction squeezing something together or like blocking out or like they're just like floating around. So they just like blob together. You know what I mean? So like when you take the oil and water and you shake it up, like the water separates because the water is squeezing together and squeezes out all of the oil. And the oil just pops up to the top, right? However, if you wanted to mix things like, I don't know, olive oil and peanut oil or whatever, I don't know, you can just like put them in the same container, give them a quick stir, and they just blend. Because there are no intermolecular forces of attraction holding like the olive oil together with the olive oil and the peanut oil with the peanut oil. There's nothing. There's no forces of attraction, so they just mix. It's like mixing red ping pong balls and white ping pong balls. You stir them up and they mix because there's nothing to keep them separate. You dig? So one of the things that we like to say is like dissolves like. And what that means is polar dissolves polar and ionic, nonpolar dissolves nonpolar and nonpolar. Right? So if you can see in this little picture, when you throw oil in there, what's actually happening is the oil is just sort of chilling. And it's not doing, like oil molecules really aren't doing anything, but what is doing something is the water. The water is actually squeezing together so hard that it just pops the oil out of the water. And that's how, and that's why oil and water kind of separate, because polar stays with polar, nonpolar stays with nonpolar, for the most part. And as always, I'm going to give you the caveat that in nature, there's the rule, like there's the way things always happen, and there are always going to be about 10 million exceptions. So, yeah, why wouldn't there be exceptions, you know? All right, so now we're going to get into factors of solubility that we can actually mess with. We can actually, like, do something about. For example, pressure. We can totally adjust the pressure on a substance, right? Problem is, pressure does absolutely nothing for a solid. No effect, right? And the reason why pressure doesn't affect a solid is because the particles in the solid are already right next to each other, right? They are like, there's no space in between the particles, so when you squeeze them, they can't get any closer together. So that has basically no effect. Now, on the other hand, gases, this is important to know, that solubility increases with more pressure, okay? And I want you to take a really fine look at this here. There's a big difference between solids and gases when it comes to solubility, right? And it's kind of like because of what we need to do to make things dissolve. If you think about it, when you take, like, I don't know, here's like a beaker, right? And we're going to pretend we have purple water, and we're going to fill it with our solid, right? We're going to throw a chunk of the solid in there, right? So to get that solid to dissolve, we want to somehow get these particles to come apart and float everywhere. Does that make sense? We want to break them apart. We want to spread them out as much as we can. Now, the sort of the opposite situation with the gas, there's some liquid here, and here's some gas particles floating around at the top here. What we want to do to get a gas to dissolve is we want to squeeze it, we want to condense, we want to confine and squeeze it down into the water. So we want to get the gas particles to sort of simmer down and head into the water. We want them to calm down and come together, because gas particles are like everywhere. And we want them to like stay within a container, like inside the water. So we got to get them to sort of like squeeze together, get into the container, simmer down, and stay. So it's the exact opposite of a solid. Solids we want to spread out everywhere. Gases we want to slow down and contain. Which is why it's like two different two different categories here. Pressure, like, well, for a solid, it doesn't really do anything because there's no space, but you can almost see for a solid, it's going to increase the solubility because you're going to literally squeeze that gas down into the liquid. Does that make sense? Good. So these like variables that affect solubility, they split into two categories, one for solid, one for gases. Got it? Awesome. Let's move on to temperature. Oh, also, when we're talking about solubility of gases, you can just think about soda, right? When it comes to pressure for a soda, you buy soda like a 2-liter bottle of Coke or something. It's under a lot of pressure, and the reason why that fresh 2-liter bottle of soda is under pressure is because that pressure squeezes the carbon dioxide into the soda and keeps it there, right? So that when we open it, it's all bubbly. Now, what other variable you want to talk about? Yeah, let's talk. Ooh, what was that? Let's talk about. Let's talk about temperature for a minute. Why not? So temperature, if you can believe it, is going to affect solids different than it'll affect gases. Because remember, solids you want to break them apart and spread everywhere. Gases you want them to simmer down and get down into the container. So that's kind of opposite. Temperature does sort of the opposite. So for a solid, the solubility will increase with more temperature, because what temperature does is it speeds the particles up, makes them move faster and faster, so they can bounce around and spread all over the place, which is exactly what you want for a solid, right? But not for a gas. You know what I mean? Not for a gas. The solubility will decrease with more temperature for a gas. So in other words, you want to keep things cold to keep gases dissolved in liquid, which again, for a soda, you put it in the fridge. If you open up a 2-liter bottle of soda and you want to put the cap back on and you want to put it in the fridge, because the refrigerator will cool it down to keep those gas particles calm and staying in their container. But if you leave it out next to I don't know, the heater or something, it's going to make it warm. The particles are going to move around more, and it's going to be really hard for those gas particles to stay in because they're moving around and they just want to fly out everywhere. You guys get what I'm saying? I know you get what I'm saying. So remember, temperature increases solid solubility, it decreases gas solubility. All right, and that brings us here to table G, which is another bit of scientific literacy. And what this tells us is the solubility of different substances at different temperatures. And now let's look at two of them. First one I want to look at here is this guy, sodium nitrate. Basically what they did here is they took 100 grams of water, like a beaker, and they filled it with 100 grams of water, and they just changed the temperature. They went to 10 degrees Celsius and they saw how much sodium nitrate they could dissolve, and they put a dot. Then they went to 20 degrees and they put a dot, and they went to 30 degrees and put a dot. So, so on and so on and so forth. So this line tells us the most that you can dissolve at any given temperature. So at 40 degrees, it looks like sodium nitrate can dissolve about 105 grams of sodium nitrate in 100 grams of water. Not bad. At 70 degrees, you can dissolve, let's do, I don't know, 130. You can dissolve 137 grams of sodium nitrate at 70 degrees. That's kind of ridiculous. That's kind of ridiculous. Now, sodium nitrate is a solid. And one way I can tell is if you look at this line, it's going up with temperature. In other words, as the temperature increases, the amount of stuff that I can dissolve, the solubility, increases. You got it? Now I want you to lay your eyes on this thing right here, ammonia. If you notice, as the temperature goes up, what happens to my solubility? Right? Or the amount that can get dissolved? Yeah, man, it's dropping. It's dropping. So this must be a gas, right? Because the solubility is decreasing with temperature. So the hotter it gets, the less can stay inside the solution. And one other thing is this line, we call this the line of saturation. These lines represent what we call the saturation point, or the point where you can't dissolve anymore at that particular temperature. Now I have to say at that particular temperature because you can see it changes with temperature, right? So at this temperature, I can dissolve this much, and at this temperature, I can dissolve that much. That is a difference. You guys get what I'm saying? Yes, you do. Let's move on, because we need to talk about saturation, right? I mean, if we got lines of saturation, we should know what saturation means. Saturation in like dissolving means saturation with like anything else, right? If something is unsaturated, it means it can hold more. If you have an unsaturated sponge, it means that sponge can hold water. If you have an unsaturated solution, it means it can dissolve more solute at that particular temperature. Now, how do you know if a solution is unsaturated? You take a little bit of the solute, you throw it in there, and if it dissolves, then what you had was an unsaturated solution. Now, the next level of complexity that we're going to look at here is saturated solution. Now, a saturated solution cannot dissolve anymore at that temperature. It's done. It's kaput. It's like at its capacity. It can dissolve no more. So, how do you test it? Well, the added solute will not dissolve, and it just falls to the bottom. This is like when you have iced tea and you've added sugar, and you add sugar, and you add sugar, and you stir it, and then like you add more sugar to it, and it just falls, and it doesn't dissolve because it's become saturated. The water cannot dissolve anymore at that particular temperature. Now, there is one more thing that we could talk about. It doesn't happen often in like normal everyday life, but it is a thing that can happen, and it is what we call super saturated. This is where we have a solution that for some reason, and we can actually make a supersaturated solution in lab, but typically they are like really hard to do, where you are actually holding more solute than it's like supposed to be able to at that temperature. So if you go up to table G and you read on the graph, like the line of saturation is like here and you're above it. It means somehow you have dissolved more than you're supposed to be able to. Now, the way you do it is you get a warm solution and you saturate it, and then you cool it down very, very slowly, very, very gently. And sometimes it hits a balance where the solute does not precipitate out. It just stays right in solution. However, as soon as you add the tiniest grain of solute, add the tiniest little crystal, everything falls out of solution. Like everything just crystallizes out. And we might even be able to like do something like that here today. All right. So this is all about like things that affect like the things that affect solubility. Once things are dissolved, we hit this thing like saturation, whether it's unsaturated, saturated, or supersaturated. And now this is how like what we can do to make it dissolve faster, rate of salvation. Now again, here we're gonna have like a factor, like here's particle size, but we have to have two separate categories. We have to have a solid category and we have to have a gas category. Because if you remember, to dissolve a solid, you want to break them apart and spread them throughout the sample. But a gas, you want to confine, contain, and slow down so they can stay in the sample, right? So when it comes to particle size, of your thing, like you're going to want to grind this up to be as small as possible, like powdered. Right? Because then you'll have the most effective collisions to break things apart and blah, 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 increasing surface area. Gas doesn't really matter because a gas you can't break down anymore. Stirring. Now here's the thing. I think stirring shakes things up, right? Really good for a solid. Very bad for a gas. It's going to decrease the rate of salvation for a gas because you're agitating it. And like gas does not want to be agitated to dissolve. You got to compress and contain, right? However, if you look right here, stirring helps dissolve a solid. You know that because you've had iced tea before. You stir it up and things dissolve a little faster if it's a solid because you're trying to break the solid apart and spread it about. Now this next one, the amount of dissolved solute. So this one thing that's going to be the same for both here. As you dissolve more and more and more, the rate of dissolving is going to decrease. It's going to slow down. Mostly because the space that there is for the solute to dissolve into the solvent gets used up. And if there are fewer spaces, it's harder to get a solute into one of those spaces. And then the last thing is temperature. Temperature, again, for a solid, you want to shake it up and move it about. It is definitely going to increase the rate of solvation for a solid, but for a gas, if you increase the temperature, it's going to make it harder and harder and harder for that gas to dissolve. You guys follow me there? I hope you are, because we got one more thing I want us to look at here before we wrap it up, and that's like table G. What are some things we can do here? So, if something is above the line, so let's look at ammonium chloride, just because it's just like right here, right? Ammonium chloride, this guy. If we have a solution of ammonium chloride in 100 grams of water at, I don't know, let's choose 60 degrees, and we have dissolved 80 grams, right? So here's our point. That's going to be above the line. Well, this line right here is the line of saturation, and it's supposed to only be able to dissolve, I don't know, what is that, 57? That's what it's only supposed to be able to dissolve 57, but somehow it's at 80. So that is going to be saturated, unsaturated, or supersaturated. Yeah, super. Supersaturated, absolutely. Now if it's right on the line, if we end up with 57 grams of ammonium chloride at 60 degrees, and we are dead on that line, well, that's the most that it can dissolve at that temperature, and that is what we call saturated. Yeah? And if it's below the line, again, 60 degrees, let's say we only dissolved 20, right? We only dissolved 20 grams. Well, that means that it has not dissolved as much as it possibly can. It is able to dissolve more. How much more? It can dissolve that much more. So if it can dissolve more, we're going to call it unsaturated. Dig? Nice. Because now we're done. Yeah, so what we're going to do is we are going to look at dissolving solids and gases. That's like going to mull the ideas around in our head, and then we have a whole bunch of work using that table G. I hope you guys had a great day. This was fun for me. I'll see you soon.